So welcome to 4Ks College of Science Education, and when you say Shungu. So in this video we'll talk about A-level chemistry. This is for our online lessons, and in this program we're going to cover a lot of things, but we will start with Equilibria, and we'll move on to talk about equilibrium constants such as Kc, Kp, Ksp. So we're going to cover a lot of ground in this series. So let's move straight to reversible reactions. So you need to understand reversible reactions before you can start to understand the concept of equilibria or equilibrium. So let's talk about reversible reactions. What are they? These are reactions which can go in the forward direction and also in the backward direction. So we represent a reversible reaction using this sign here. So let's look at a generic example here where you have A plus B reacting to form C plus D. You have your reactants A and B reacting to form C and D, your products. But you should also take note here that since it's a reversible reaction, C and D can also react in a backward reaction here to form your A and B. So these are the reactants in the forward reaction, and C and D are the reactants in the backward reaction, where your products are A and B. Alright, so let's keep that in mind. So what happens here, if you were to look at the concentration of A and B over time, you would realize that the concentration of A and B would begin at a high level here. So you're going to have a high concentration of A and B at the beginning. And as the reaction progresses, the concentration will decrease up to this stage where the concentration is constant. So this is what happens in the forward reaction. You are going to have your reaction happening quickly at the beginning because you have a high concentration of A and B, which progressively decreases over time, and hence your speed of reaction for the forward reaction will also decrease over time. Let's see what happens in the backward reaction. In the backward reaction, you have your C and D. So initially, you have 0 C and D. But as the forward reaction progresses, you are going to form C and D, and you're going to begin with a small concentration of C and D. And what happens is that as the reaction continues to progress, I'm talking about the forward reaction here, as it continues to progress, C and D will increase in concentration, and as C and D increases in concentration, the speed of reaction of the backward reaction will also increase. So you see here progressively the concentrations of C and D increasing up to this stage where they are constant. And you should also note that progressively the speed of this backward reaction is also increasing. It begins at a low speed and it increases progressively. Okay, so let's look at this stage here where the concentrations are constant. So this is called dynamic equilibrium. So at this point, the rate of the forward reaction equals the rate of the backward reaction, and it is called dynamic equilibrium. And we should note here, like we said, the concentrations are now constant. So the concentrations of each substance remain constant. So this is important to note for this stage called dynamic equilibrium. And here it's important to note here that this is not the same as amount of reactant, and it doesn't mean that when we get to this stage the amount of reactant and the amount of product is the same. This is not the case. We are simply saying the speed of the forward reaction is equal to the speed of the backward reaction, and the concentrations remain constant. It doesn't mean the ratio of the concentrations is 1:1. It may be 1:2, 1:4. It doesn't mean the amount of the product is equal to the amount of the reactant. This is not the case. Okay, so let's also take note that this state is only possible when you have a closed system. This doesn't work where you have, say, one of the products is a gas and it vaporizes, it diffuses into the atmosphere. This is not going to be attainable if you lose the products, such as in a gaseous reaction. So you need to have a closed system. Let's talk about Le-Chatelain's principle, which is important to this concept of dynamic equilibrium or just equilibria in general. So Le-Chatelain developed a principle where he stated what would happen if we change the conditions to an equilibrium reaction. So if you were to change one of the conditions in terms of temperature, pressure, or concentrations, what happens? It is Le-Chatelain who proposed what would happen. So let's look at what he said in his principle, Le-Chatelain's principle. If a reaction at equilibrium is subjected to a change in pressure, temperature, or concentration, the position of equilibrium will move to counteract the change. You can replace this word with to minimize the change. So if you change pressure, temperature, or concentration, then your equilibrium is going to shift so as to minimize that change. Let's look at this in more detail. So you have two possibilities here. You can change a condition that results in the equilibrium moving to the left. So this is the position that we are referring to here. It can be that it moves to the left. So the left here represents the reactants. So in this reaction that we're looking at here, if the position moves to the left, it means that we will make more of the hydrogen and nitrogen. We'll make more of the reactants. We can also change conditions to enable the equilibrium position to shift to the right. So when the equilibrium position shifts to the right, it means we are forming, in this case, more of this product here. So this is what happens according to Le-Chatelain's principle. You can shift the position of the equilibrium to the left or to the right. Okay, so let's look at conditions that might cause this to happen. So let's talk about concentration. If we increase the concentration of a reactant or product, the equilibrium will shift to try and reduce the concentration. So if you increase the concentration, the equilibrium will try to reduce. It will shift in the direction that causes the concentration to reduce. So let's look at this situation here. If you increase the concentration of hydrogen, so let's focus on hydrogen here. If you increase the concentration of hydrogen, the equilibrium will shift to the right. So it will shift where? To this direction, and it will produce more of the NH3. If I increase this concentration, the system is going to try and reduce the concentration. How does it do so? It does so by using up the extra H2, and it uses up this extra H2 to form the NH3. So it will shift towards the right. Okay, you can also cause it to shift in the left direction. So if you increase the concentration of this NH3, the system will try to reduce the concentration of the NH3, in which case it moves towards the formation of nitrogen and hydrogen. Thus it shifts to the left. So you need to be able to interpret whether your equilibrium is going to shift to the right or to the left. So in the next part, we'll look at other conditions such as pressure. We'll also look at temperature for this Haber process. So let's try to quickly go through what would happen if I increased here my pressure. Okay, if you increase the pressure, the equilibrium here will shift in the direction, will shift to the side with the fewest number of gas particles. So remember, the more gas particles you have, the higher the pressure. So if you increase the pressure, the equilibrium will shift to the side with the fewest gas particles. What does this mean? If you have few gas particles, then your pressure is going to decrease. So in other words, the system here is trying to reduce the pressure. You increase the pressure, the system tries to reduce by shifting to the side where you have the fewest gas particles. So let's look at the particles. You have 3 moles here, and 1 more, you have 4. This side you have 2. So it means that the direction of the equilibrium is going to be towards your right, this side where you have few particles. And the reverse is true. If you decrease the pressure, it will move to the left. So you need to be able to interpret what would happen according to Le-Chatelain's principle. So next we'll talk about temperature. So see you in the next video.